Hello friends and welcome to this video. In this video, we are going to study about the ResUNet++ and then we are going to implement it in the TensorFlow framework. So let's get started. First of all, a simple starting of the ResUNet++. So it is a semantic segmentation architecture that take advantage of the following block. First is the residual block. Second, squeeze and excitation block. Third, arterial spatial pyramidal pooling. And the last one is attention block. So now we'll take a look at the architecture, that is the block diagram given in the original paper. So here you can see we have the input, and after that we have the encoding block, that is the encoder, and between encoder and the decoder we have the ASPP, that is the bridge which joins both encoder and the decoder. After the bridge we have the decoder block, and the decoder blocks gives you the segmentation mask. Now we are going to implement it, so let's get started. So first of all, we'll import the TensorFlow library. Now we'll start with the implementation of squeeze and excitation block. So first of all, we are going to define the name of the function, that is SE. SE takes the input feature map and ratio equals to 0.8. Now the shape of the input would be something like this. First would be batch size, let's say 8, then height, then width, then number of channel, let's say 32. Okay, now if you can here see, these are the number of feature channel and they are on the last axis. So we have another variable called channel axis and its value is -1, that is the last of this list. Now we need to calculate the number of filter and these are on the last axis. So we would have inputs dot shape and last axis, that is the channel axis. So this way we get the number of filters. Now we have SE shape. So this is 1 by 1 by number of filters. So our first layer is global average pooling layer. So it's going to apply a average pooling over the entire feature map. So you can imagine the window size of this would be equals to the height and width of the input feature map. So X is the output and this is the input. So now the output shape would be equals to batch size by number of channels. Next we are going to reshape it. So we're going to say L dot reshape, then we provided the proper shape, and then X, that is the output of previous layer, that is global average pooling layer. Next we have two dense layer. So the first dense layer we are going to decrease the number of features by a factor of this ratio, or we can say by a factor of 8. Okay, and here we have relu as the activation function and we have set bias to false. Next we have one more dense layer where we have used sigmoid as the activation function to provide attention to the input feature map, and here the number of feature are equals to the number of features in the input. So next we are going to multiply both of them. We multiply the input, the original input feature, and the output of this last dense layer where we applied sigmoid activation function. So the important feature of this sigmoid activation function is that you give it any value and it's going to convert it in the range of 0 and 1. Here this 0 and 1 determine the importance of each channel in this input feature map. So you can imagine a value, that is the output of this layer, if it would be in the range of 0 and 1, the closer it is to 1, the important that channel, and the closer it is to 0, the less important is that channel. So that's how it works. Basically for each channel it's going to give you an individual value, a single individual value, and it's going to multiply that entire channel with that single value. So imagine it something like this. Let's say you have a channel value, let's say 10. Okay, now if you multiply, let's say the value of X for this channel, or that specific value is 0, It's going to become 0. So this indicate this channel is not important, so its value became from 10, it became to 0. But let's say it's the value of the attention here is 1, so it remains exactly same. So in this way it's gonna suppress the feature channels which are not required accordingly. Okay, so that's how the squeeze and excitation work. So this is done, squeeze and excitation. Now we're going to work on the stem block. So here, this is the original diagram, block diagram. So this first block, it is called stem block in the original paper and also in the code. So here you can see the layers. First we have conv layer, then we have base normalization and ReLU, then again a conv layer, and we add. Then we have a shortcut. So this shortcut basically represents a 1 by 1 convolution and batch normalization, and we add them. Okay, after that we have squeeze and excitation. So let me follow it. Let's move back to our okay. So we would have a function called stem block. It take your input to feature map, number of filter, and the stride value. So here one more thing, if we have note about this architecture, it does not use any max pool layer. So to reduce the height and width of the feature map in the encoder, it uses strided convolution, and in this stem block it does not use any strided convolution. Strided convolution are used in the rest of the encoder block. Like in these 3 blocks, it uses strided convolution to decrease the size of the feature map, that is the height and width. So we have first conv layer, and I'm going to copy them. So this is first conv layer. Okay, its stride value is 1. Then it has base normalization and a ReLU activation function. After that it has a conv layer again. Here the stride value is same, that is the default value. Even you can remove it here if you want. You can also keep it like this, so it won't have any issue. Next we have that shortcut. You see in this diagram, this shortcut. Let's move back to our editor. Now we're going to add both the features, that is the X and the S. Okay, now if you again see, now it is, these arrows are basically moving to the decoder block, and after those arrows we have SE, squeeze and excitation block. So let's do one thing, we're gonna have SE here, we're gonna call it S, and we're gonna call SE layer, and we're gonna give X as the input. So we're gonna get 2 values. First is the X, that is going to be the input for your decoder block, and the S, that is output of squeeze and excitation block, would be input for your next layer. Okay, so the stem block is done. Now we'll move on to the next block, that is this. We have batch normalization and ReLU, then we have conv, then we have batch normalization, conv, and then addition, and this arrow represent 1 by 1 conv. Okay, and these blocks are repeating, so we're going to have a single block called ResNet block. So this is the ResNet block, and here we have input, then the number of filters. Let's change it to number of filters, and a stride value of 1, and this value can change accordingly. So first conv layer. So we have batch normalization, then activation, and then convolution layer. Then we have second conv layer. Again Best normalization, ReLU activation, and convolution layer. Now we have the shortcut. Okay, so now let's move back to the diagram. After the addition, we have again skip connection to the decoder, and then we have squeeze and excitation. But if we see in the last block, we don't have SE. So let me make a few changes and move SE to the starting of this block. And I think that would be more reasonable. So let me just remove some complexities from here. And let's do it this way. X is equals to SE. Something like this. You're gonna give input to this and X to this. Okay. Now in this way, squeeze and excitation would be at the starting of every block. Okay, and the one by one all is this shortcut connection is also followed by the squeeze and excitation. So let me just change a bit. So I think things are done. First we have SE, then we have one conv layer, and again second conv layer. So let me call it inputs now, because now otherwise it would be confused at the end, which is the original input, because this SE now would act as the input for shortcut. Let me check it again. Yeah, this is right. So now we are going to add it and give our output return. So we are done with the encoder part. And encoder is really simple. Next we have is the ASPP, that is in between the encoder and the decoder, and also at the third decoder block. After third decoder, this is first decoder, then second decoder, then third decoder, we have ASPP. So let us also implement the ASPP. So in ASPP, we first have the input feature map, then we have number of filters. And here we are going to use the dilated convolution. These code all are implemented by the author, and I have taken from there. So there may be few things that would not make sense to you, but that is the original code. So first we have a conv layer, and here you can see the dilation rate is 6. Then we have second layer, where we have dilation rate as 12. Then third layer, where the dilation rate is 18. So this is 16, 12, and 18. Then in a fourth layer, it's a dilation rate with 1. So this is the default value. Next, we're gonna add them, and we get our value in the form of y, and then it is followed by the one by one conv layer. So this is our ASPP block. Okay, now let's move on to the implementation of the ResUNet++. So this is the name of our function, ResUNet PP. We have input shape. So first of all, we'll define an input layer. So this input layer would have a specific shape, and here it would be like 256 by 256 by 3. That is an RGB image. Now we have our encoder. So these are the 4 blocks as mentioned in the original paper, 4 blocks. So first is a stem block. We take input layer, then 16 as the number of channel, stride value, and we have removed this, so we're going to remove it. And from the second, third, and fourth block, it uses stride value of 2. So let us again go, and here you can see in the first conv layer we have a stride value of 2, and in the shortcut also we have a stride value of 2. So that's how it reduce the height and width of the feature map. Okay, so now comes to the bridge part where we are using ASPP. So this is now done. Now we are move on to the decoder part. Okay, so let's take a look at the diagram. So first it has attention, then upsampling, then concatenation, and after that our ResNet block. And in the decoder, in the decoder part, the ResNet don't use a stride value of 2, it uses a stride value of 1, because we do not want to again downsample the feature map. Okay, so first of all we'll implement the attention block first, because that is what is left now out of all the blocks. So in the attention block it take two features, x1 and x2. So x1 is basically feature from encoder block, and x2 is basically feature from previous block. So here if we have first decoder block and here we have attention block. So first we have b1 as the x2 and c4 as the x1, or you can say c3 as the x1. Okay, so let me go back. So now we need number of filters from the x2 part, x2 feature map. So in the x1 we have few layers, so we're going to call them x1 con. So it starts with base normalization, ReLU activation function, then we have con layer, and then as a 2x2 max pool layer. Okay, just to decrease the feature map by a factor of 2, because the size of both these feature map are not same. So let's say if the shape of this x1 is 128 by 128, then the shape of x2 would be 64 by 64, just to make sure the shape of both these feature maps are same. Then we have x2, it also have base normalization layer, ReLU activation function, and a convolution layer. Next we add both of them, that is x1 pool and x2 con. Now this output, the feature map would again followed by few layers, that is base normalization, ReLU activation function, and con 2D layer. Now we multiply this x with the x2 and we get that value back. Okay, this is attention block. Now we'll move on to the decoder part. So first would be our attention block, that is what is missing till now. Next would be a 2x2 upsampling. After that we have a concatenation with the skip connection. So the skip connection should remain same, that is c3, c3 in both the case. If you see, next is the ResNet block. So this is our first decoder block. So like this we have two more decoder blocks. Now we have our output block. In the output block we have ASPP, then a 1x1 convolution, and at last a sigmoid activation function. So now we have both the input and the output, and we're going to build our model. So let's try to run this now. So let's run this. Okay, so we have some issues. Strides is not defined, like, or the stem block. Okay, that's a mistake. In the stride block I have removed stride, and it should also be removed from here. Okay, that's the issue. Okay, let me run it again. Again, some spelling mistake happened during copy pasting. See, we always gonna have these errors, so you need to learn how to work with these errors. If you see ResNet start from line number 135, then 101, and at last line number 49. Just move on to line number 49. Should be number of filters. That's the error. So this is how you check where the error is. And now you can see it's working. You can see the segmentation mask at the end. And if you go above, you will see all the layers which we have defined now and the input. I hope this is all about the ResUNet++. So that's all for this video. Thank you. Have a nice day.